Hello dear students. So this is our another lecture on these differential equations, and today's topic is because our main focus will be on only the problems related to different topics in mathematical physics, right? So today's topic is so we have one problem. We need to show that the this legendary differential equation may be put in self-adjoint form by multiplying by some factor 1 minus x squared, right? So before that, so if we take, we have different types of homogeneous second order differential equations, and so the condition for this self-adjointness is that the coefficient of the first second derivative should be equal to the derivative of first one should be equal to the coefficient of the first derivative, right? So if you remember that, so we have this differential equation. So our differential equation is that this legendary differential equation is that's 1 minus x square, or you can write it this way. That's y double dash plus this is minus here. So this is our this legendary differential equation, right? So what I'm saying that the question says that we need to multiply this differential equation by the factor 1 divided by 1 minus x square. So that means our differential equation is that's y double dash, because when we multiply by 1 minus x square, or you can write this as y double dash So this was this legendary differential equation when we multiply by a factor of 1 divided by 1 minus x square. Now we need to prove that this differential equation may be put in self-adjointness form, because we know that, so in classwork we have discussed about, so what is the condition for a differential equation to be self-adjoint. So the criteria is that the coefficient of this first one, if you take the derivative of that, should be equal to the coefficient of the second. So that means if you put that, so because if we have some differential equation like p0 of x, y double dash, so if, so then this equation is, so this equation is self-adjoint, or we can say that like in quantum mechanics we are saying that if you take the Dagger of some operator, so if it is a Dagger equal to a, we can say it's summation, or it's sometimes called a self-adjoint, right? So we are basically in mathematics where talk about these different differential operators, we can also prove that whether it is self-adjoint or not, or if it is not self-adjoint, so we need to multiply it by some factor. So that factor is basically, we need to multiply by a factor that's y of x equal to, that's p0 inverse. So by multiplying by this factor w of x to our differential equation, so we can convert our differential equation into the self-adjoint form. So as I already told you, the condition for this self-adjointness is that the derivative of the first coefficient should be equal to the coefficient of the first derivative. That means p0 dash of x should be equal to p1 of x, right? So let's have a look on this equation. तो अगर हम ये इक्वेशन देखेंगे, because the question says that we need to multiply it by some factor 1 divided by 1 minus x square, and our final equation becomes this one, right? So this is our final equation, and we need to prove that this is self-adjoint. So if it is So if it is self-adjoint, then it's okay. If it is not self-adjoint, so can we put it in that self-adjoint form or not, right? Because this is as per the question demands us. So first of all, let us check that. So if we have this equation, so in this equation you can verify, because our P0 of x will be, so you just check that P0 of x is basically the coefficient to the second derivative. So that means the coefficient to the first second derivative is, so that means P0 of x is equal to, or you can write this as, okay, so okay, you can write this as P0 of x is equal to 1 and P1 of x is equal to, right? So because from this equation, our P0 of x is equal to 1 and our P1 of x is equal to minus 2x divided by 1 minus x square, right? So from this, so we need to verify that if P dash of x is equal to P1 of x, so then it is in the self-adjoint form. If it is not, so we need to multiply it by a factor of w of x, right? Because so it is clear, if you take the derivative of this, so it will be 0, right? So that means we can from this we can have, so p0 dash of x is not equal to p1 of x. So that means this condition is not satisfied here. So we can say that this differential equation is not in self-adjoint form, right? So we need to convert it into the self-adjoint form by multiplying by this factor, that is w of x equal to, that's p0 inverse. Here is for integral of p1 of x divided by p0 of x d of x, right? So we need to multiply this factor to our differential equation and we can convert it into the self-adjoint form. So first of all, let's have a look on this w of x. So the form of w of x is this one. So you know what's p0 of x, so from that equation, so you know what's p0 of x, so that is equal to 1 and p1 of x equal to minus 2x by 1 minus x square. So we will first calculate that w of x from this equation and then multiply it over main equation, and then we can check whether it is self-adjoint or not. तो पहले अगर हम इस इक्वेशन में लिखेंगे p0 of x is equal to 1 and p1 of x is equal to this 2. So let's calculate w of x. So w of x will be equal to, right? So this is because our p1 of x is equal to, तो आप यहाँ पे देख सकते हो जो हमारा p1 of x है, that is minus 2x upon 1 minus x square, and p0 of x is equal to 1, right? So this is what I did here. So because it is for p1 of x divided by p0 of x divided by x, or you can write this as, so this will be equal to minus, or you can put that 1 minus x square as t. Okay, because you can do the substitution. So that means w of x will be equal to, right? Because this will be that dt by t, and when you integrate this, so this will be ln of t. So ln and this, these are inverse of each other. So you can write that t, but then do that substitution, that t equal to 1 minus x square. And now, so that means we need to multiply this factor, because in classwork we have discussed that, so how to convert a differential equation into the self-adjoint form by multiplying by this factor w of x, right? And from this differential equation, so from you can also because if it is this operator is self-adjoint, so from that equation we can say that, because from the condition of this Sturm-Liouville's problem, you can construct a set of orthogonal functions from the differential equation. Because we have discussed that, I cannot say, I cannot talk about that thing, anything. I cannot continue that, because we have discussed that Sturm-Liouville's problem. So that's a Botrel value problem. So we have discussed that, and we can construct from that from Sturm-Liouville's condition that set of those orthogonal functions, right? Because it's clear. So that's clear, right? Now we need to multiply this w of x over this equation. So that means जो हमारी main equation है, that is w of x y double dash of x minus this term equal to 0. तो इसको मुझे multiply करना है w of x से. So but w of x is our that is equal to 1 minus x square. So when I multiply this equation by 1 minus x square, so my equation becomes, because my equation was, so you can write that w of x तो ये हमारी इक्वेशन थी and I multiplying it by w of x, right? Because it's clear. Now w of x we know that we have calculated the value of w of x, that's 1 minus x square. तो इसको हम substitute यहाँ पे करेंगे, so that means I will get here equal to 0, because 1 minus x square will cancel from the second and the third term, and first term will be 1 minus x square, right? So that's it. So we need to check now. Let's have a quick check that whether this differential equation that we get after multiplying by w of x, whether it is self-adjoint or not. So for the condition of for a differential equation to be self-adjoint, so we need to, it should fulfill one criteria, that p0 dash of x should be equal to p1 of x, right? But we know that from here, what's p0 of x? Because here p0 dash of x is equal to, that's p1 of x. When you differentiate this term, so that's minus 2x, that's equal to p1 of x. So we are getting basically, so we can say that our differential equation, therefore that differential equation is, so which equation? So that is basically this equation. So जो हमारी differential equation A है, it becomes now self-adjoint, right? Because it fulfills this criteria that p0 dash of x is equal to p1 of x, right? Similarly, we can have a set of differential equations, and one more that differential equation that comes in my mind, that is Bessel differential equation, right? So another differential equation. Let's have a look on this. So the question says, it is basically the repetition. So we're again discussing the same, that this method, but for a second kind of differential equation, right? So the question says that show that the Bessel differential equation may be put in this self-adjoint form. So first of all, so we know that the form of the Bessel differential equation. So let me write first so Bessel differential equation you can define by, so that is x square y double dash equals. So ये हमारी Bessel differential equation है. Let's have a look first, because the question says that can we put it in self-adjoint form or not. So first of all, we are saying that we need to make a quick check whether this differential equation is self-adjoint or not. So for that we need to prove that, because from here what's our p0 of x? So that's x square, and p1 of x equal to, that's x. So which implies that p0 dash of x is not equal to p1 of x. So ये same नहीं है, because it's clear, because when you differentiate this p0 of x, it is twice x, and 2x cannot be equal to x, right? So this differential equation is not in self-adjoint form. So as I already told you, and we have already discussed in our classwork, that to make this differential equation this self-adjoint, so we need to multiply it by some factor, that is w of x, and that basically makes it makes this differential equation in self-adjoint form. So first of all, let's calculate what should be our W of x, right? Because this is clear from this condition that this is not in self-adjoint form. So let's first calculate W of x. So W of x you can write by, that's P0 inverse. Okay. So P0 of x is, that's, or you can write this as x square whole inverse, because P0 of x is our x square e power. Okay. This will be equal to, right? So when you integrate this, because this is integration of 1 by x, so it is log of x, and that log and e cancel, so you will get that ex here. So we can write that the W of x will be equal to, so what was there? So that is 1 by x square. So that means in order to make this differential equation in self-adjoint form, we need to multiply the differential equation by this factor, that is W of x. And we have calculated that W of x is our 1 by x. So that means you have a differential equation here. So this differential equation, we need to multiply it by factor W of x. And W of x we have calculated its value is 1 by x. So we need to multiply this by 1 by x in order to make it self-adjoint. Okay, so first let's write that differential equation by multiplying by W of x to this differential equation. That's x square. Because when you multiply this differential equation by the term 1 by x, so first term gets, you can get one x will cancel, so you will get here one, here x y double dash, and this x will cancel for the second term, and you will get y dash of x, and the third term, because you need to divide that x with the whole term, so first will be then x, then minus m square by x whole of y, that's equal to 0. And now we have to make a quick check that whether this differential equation is in self-adjoint form or not, or whether the operator, corresponding operator, is Hermitian or not, or we can say that it is self-adjoint or not. So you can interpret it in many ways, right? Now, first of all, let's have a look. So, what's our P0 of x from here? So, our P0 of x is that's equal to x, and P1 of x is equal to 1, right? So, let us check the basic criteria for a differential equation to be self-adjoint. So, we need to check the criteria that P0 dash of x equal to P1 of x. So, because from here, so if you calculate what's P0 dash of x, so that's equal to 1, but that's equal to P1 of x. So that means this differential equation, this differential equation, this equation A, so this equation A is self-adjoint. Because it basically fulfills this criteria, so this is that's it. Okay. And similarly, I cannot repeat the whole process, but I can make a quick look on the other types of differential equation. If you talk about this liquid differential equation or the Hermite polynomial, so you can also verify that if these are not in self-adjoint form, you can put it in self-adjoint form. So let's have a quick look on one more differential equation. So you can do it yourself, but at least I will first I will calculate that factor w of x, then it's okay. Because we have one more example. If you take some Lagrange polynomial, so we have this, that's xy double dash plus 1 minus x x of y. So this is our Lagrange differential equation, right? And similarly, first let us check whether this is in self-adjoint form or not. So because p0 of x is equal to, so that's x 1 minus x, right? So here p0 dash of x equal to 1, that's not equal to p1 of x. So that means this equation, so this above equation is not in self-adjoint form, right? So in order to convert this in self-adjoint form, so we need to calculate this factor. That's w of x, that's p0 inverse. Right? Or you can write that because p0 inverse is p0 inverse, that's 1. So it is 1 inverse. And p1 of x is equal to, that's 1 minus x upon, sorry, this is this x here, sorry, x inverse x. Okay, this can be right, you can rewrite this as 1 by x. Because we can split this exponential term into two terms. So first term will be, because when you write that x1 with that x, so you can get that 1 by x d of x. And similarly, the second term from here, it will be that's minus 1, because it will be minus x by x. So that's minus d of x, right? Now integrate this equation, you can have this ln of x, here it will be simply x, right? So that means our w of x will be, so this will be equal to, let's have 1 by x. Right? So that means w of x जो हमारा है, that's basically 1 by e raised by x, right? So from this, when I calculate that w of x, in order to make this differential equation in self-adjoint form. Now we can multiply this w of x over this differential equation. So our differential equation is basically this one, that's Lagrange differential equation. You need to multiply it by w of x in order to convert it into the self-adjoint form. So we can add that w of x, and inside will be, that's equal to 0. Okay. So from this equation, so first we need to check now whether this is self-adjoint or not. So first let's see what's p0 of x. So p0 of x is our x e raised by x, and p1 of x is our 1 minus x divided by e raised by x, right? So So we can write now. So P0 of x is, that's x e power x, x, right? So first let's calculate what's P0 dash of x. So that is e power x minus x e power x upon x. You can use that quotient rule by differentiating this p by q form and you will get this. Okay, or you can write this as 1 minus x upon e power x, because you can take 1 e raised for x common, so inside will be 1 minus x, so divided by e raised for x square, so this will be 1 minus x divided by e raised for x. So that means our w of x is this, and when you multiply this w of x to our main differential, to our original differential equation, so that differential equation will be then that will be in self-adjoint form. So you can write that. So because you need to multiply, so we have already done that, right? So we are calculating that p0 dash of x, right? So p0 dash of x is this thing, but p1 of x is this, right? So that means therefore p0 dash of x will be equal to p1 of x, right? So that means this equation is now, so this equation b, so equation b is in that's right. So this was similarly, if you can check for many other differential equations, if you go through different textbooks on this mathematical physics, and you can see whether the differential equation can be put in this self-adjoint form or not. In addition to that, I have already talked about that when we put some differential equation in, if it is in self-adjoint form, so from the Lewis boundary conditions, you can say that Sturm-Lewis problem. So from this differential equation, then we can construct the condition of orthogonality, right? So we can have some set of orthogonal functions. So the product of those functions will be 0, right? If you take some function yn and ym and solve this differential equation, and you can get some those orthogonal conditions with the help of that, which is what is called as Sturm-Lewis problem. तो हमने already discuss किया है class work में, तो I cannot discuss that. So, but you can do many other things related to these differential equations. Thank you very much.